This is the AP Statistics Chapter 5 Test Review. A computer company makes desktop and laptop computers at factories in 3 states: California, Texas, and New York. The California company produces 40% of the company's computers. The Texas factory makes 25%, and the remaining 35% are manufactured in New York. Of the computers that are made in California, 75% are laptops, 70% are laptops in Texas, and 50% of them are laptops that are made in New York. All computers are first shipped to a distribution center in Missouri before they are sent out to the stores. Suppose we select a computer at random from the distribution center. Construct a tree diagram to represent this situation. So we know California is 40%, Texas makes 25%, and the last 35% come from New York. So in our tree diagram, we have 3 different factories. We have one in California, one in Texas, and one in New York. We know that 40% of them are made in California. We know that 25% of them are made in Texas, and the remaining 35 are made in New York. Now we know that in each factory, they make laptops and desktops. We know that in California, 75% of them are laptops. In Texas, we have 70%. In New York, we have 50%. So in California, we know that 75% of them are laptops, which means 25% of them are not. In Texas, we know that 70% are laptops, which means 30% are not. And in New York, we know that 50% are laptops, so the other 50% will not be laptops. If we choose a computer produced by one of these 3 factories, what's the probability that it is a laptop? Show your work. So if we want to find the probability that they're a laptop, let's find all the probabilities first. Now on these tree diagrams, we're saying that they're made in California and that they're a laptop. So to find that probability, and means that we are going to multiply. So 0.40 times 0.75 gives us 0.30. And if we find each of these probabilities, remember, if we add all of them together, they should add up to 100%. Now, we're just looking for the ones where they are laptops. So we have a laptop here, they are a laptop here, and they are a laptop here. So we will add those probabilities together. And that's going to give us a probability of 65% that if we randomly select a computer, that it will be a laptop. If a computer is selected is a laptop, what factory is it most likely to have been produced? So we do know that it is a laptop, and they can come from California, Texas, or New York. Now, the ones in California are 30% of the laptops. So 30% over the 65% that are laptops, 30 divided by 65, will tell us that 46% of them are made in California. Of the 65% that are laptops, we know that 17.5% of them are made in Texas. So 0.175 divided by 0.65 is going to give us 0.27, or 27% of the laptops are made in Texas. And in New York, we know, again, that 65% of the computers are laptops. Of those, 0.175, or 17.5% of them, are made in New York. So 0.175 divided by 0.65 will tell us 0.27, or 27% are made in New York. So we know 46% of the computers are made in California. We know that 27% are made in Texas, and 27% of the laptops are made in New York. So that most of them are made in California. So if you were to choose them, a laptop, randomly, the best chance of selecting one would be from California, which is 46% of the computers. Your teacher invented a fair dice game to play. Here's how it works. Your teacher rolls one fair-sided orange die, and you roll one fair-sided blue die. Each player rolls once. If the sum of the two die are even, you are going to win. And if the sum of the die are odd, your teacher will win. Here is the sample space below. So let A be the event that you win. Find the probability of event A. So we know that you win if the sum is even. So we know the sum will be even. 1 plus 1 gives us 2. So all of these events will have sums that are even. Now we know that there are 36 possibilities in this sample space, and half of them will have sums that are even. So we know the probability of you winning is 18 out of 36, or 50%. Let B be the event that you get a 2 on your roll. Find the probability of A or B. Now, we know that you are rolling the blue die. So the probability that you roll a 2 is just here. So we know that that is 6 out of the 36. Or, if we write that as a decimal, 0.16 repeating. Are events A and B independent? Justify your answer. So to see if they're independent, we need to see if the probability of B given A is equal to the probability of event B. Now we said that event B was 0.16, but we need to find the probability of A and B for part B. A or B, sorry. So this means that either you win or you roll a 2. Now we know for part B that you win 18 out of 36 times, and we know that you can roll a 2 6 out of 36 times, but those are not mutually exclusive events. The chance that both of those things can happen, you win and you roll a 2 here, here, and here, so we need to subtract out that probability. And that would give you a probability of A or B is 21 out of 36, or approximately 58.3% of the time. Now let's go back to that probability of B given A. So the probability of A, the probability that you win, is 18 out of the 36. So given that you are going to roll a sum that is even, there are 18 times that you do that. So the probability of B given A, there are 18 times. Out of those 18 times, 3 of them you will roll a 2. So 3 out of 18 gives us 0.16 repeating. We already found up here that the probability of event B is also 0.16 repeating. So since the probability of B is the same as the probability of B given A, we do know these events are independent. Researchers are interested in the relationship between heavy drinking and cirrhosis of the liver. Suppose an adult male is randomly selected from a particular population. The following table shows the probability of some events related to this chance process. So the probability that someone is a heavy drinker is about 4.6%. The probability that they're a heavy drinker and get cirrhosis of the liver is 1.2%. And the probability that they're not a heavy drinker and they don't get cirrhosis is 0.936. We need to make a Venn diagram. So if we make ourselves a Venn diagram, we can have people who are a heavy drinker, people who get cirrhosis, and people that it does not apply to at all. So we said that 93.6% are not heavy drinkers and do not get cirrhosis of the liver. So that's going to be the part that is outside of the circles. We know the percent that are heavy drinkers and get cirrhosis is 0.012. We know the percent of the people who are heavy drinkers is 0.046. Now, that if they are a heavy drinker, they can be a heavy drinker and get cirrhosis of the liver. So if we subtract out the probability that they do get cirrhosis and are a heavy drinker, that's going to leave us with 0.034% just in the heavy drinking does not get cirrhosis. Now remember, in the whole thing, we should add up to 100%. So if we have 3.4% who are just heavy drinkers, 1.2% who are heavy drinkers and get cirrhosis, and we know that 93.6% are not heavy drinkers and don't get cirrhosis, that's going to leave us with 1.8% who get cirrhosis but were not heavy drinkers. Find the probability that the individual gets cirrhosis given he is a heavy drinker. Show your work. So given that he's a heavy drinker, we know total in that category, we have 3.4% and 1.2%. That's going to give us 4.6% total. What percent of them actually do get cirrhosis? We said was 1.2%. That's the part in the overlap. And if we divide that out, we're going to get 26%. So 26% of heavy drinkers will get cirrhosis of the liver. Find the probability that the individual is a heavy drinker or gets cirrhosis of the liver. Show your work. Now, showing your work on this, if you have a Venn diagram, is much easier because you can just add those categories. So they are just a heavy drinker, or they're a heavy drinker who gets cirrhosis, or they just get cirrhosis. We can just add those categories. So 3.4% plus 1.2% plus 1.8% will give us 0.064 or 6.4%. The other way you could have looked at this is you could have just said 1 minus the probability they don't have any of those conditions, and that'll still give you that 6.4%. 2 adult males are selected at random. Find the probability that at least one of the two gets cirrhosis. So we have 2 males. The probability that at least one of them is kind of hard to find. So what we can do instead is find the probability that neither of the men get cirrhosis of the liver. Now, we know that the probability that the first one does not get cirrhosis is 0.936, and we know that the health of one man does not affect the health of the other man, so the probability the other man does not get cirrhosis is also 0.936. We can multiply these two events together, and the probability that neither of the men get cirrhosis of the liver is about 87.6%. To find the probability that at least one of them gets cirrhosis, that means the first guy could get it, the second guy could get it, or they could both get it, we can just do 1 minus the probability that neither of them get it. And that gives us about a 12.39% chance that at least one of them will have cirrhosis of the liver. Based on previous records, 10% of the world's population is left-handed. A board secretary decides to pass the time by calculating how many visitors sign in to her workplace it takes until she sees 2 people who are left-handed. Describe the design of a simulation to estimate the average number of visitors it takes to find 2 who are left-handed. Explain clearly how we use the portion of the table of random digits below to carry out your simulation. So first, we need to describe the design simulation. So let's let numbers 0, 1 to 10 represent left-handed people, and 11 to 99 and the number 00 represent right-handed people. We are going to divide the digits into 2-digit increments and count the number of people are needed to get 2 people who are between 0, 1, and 10. Once this is completed, we will continue on the same line to start our next simulation. So we're going to perform 3 repetitions of a simulation you described in part A. So we need to mark directly on this. So we are going to divide them into 2-digit increments. So 75 is not in the right place, but 1 is. So we already have 2 people. So that took us 5 people to find 2 who were left-handed. Now, let's do it again. So we have to do this for 3 simulations. That time, it took her 27 people before she got 2 left-handed people. And if we do this one more time, that time it only took her 4 people. So those are 3 separate repetitions of our simulation. 1,000 students at a city high school were classified according to their GPA and whether or not they consistently skipped classes. The two-way table below summarizes the data. So the first thing we need to do before we answer any of this is to create a totals row and a totals column. This will make our calculations much easier. So what's the probability that a student has a GPA over 3.0? So total, out of the people who got a 3.0, there were 270 people who got over 3.0 out of the 1,000 students. So the probability is 27%. What's the probability that a student has a GPA over 3.0 or has skipped a few classes? Now, we know the probability that they got over 3.0 is 270 out of 1,000. The probability they skip few classes is 890 out of 1,000, but it is possible they skip few classes and have over 3.0. So you have to subtract where those two overlap. And the number of people who have over 3.0 and skip few classes is 265 out of the 1,000, which will give us a total of 895 students out of the 1,000 skip few classes and have over 3.0, or 89.5% of the students. What is the probability that a student has a GPA over 3.0 given that he or she has skipped few classes? So we know they skipped few classes, so that's only 890 of the students. And of those 890, how many of them have a GPA over 3.0? And that's 265. And that gives us 29.8% of the students who skipped few classes had over a 3.0. Distance learning courses are rapidly gaining popularity among college students. Randomly select an undergraduate student who is taking distance learning course for credit and record the student's age. Here's the probability model. Find the probability that the chosen student is not in the traditional age group of 18 to 23. So there's two ways you can do this. We know the percent that is in that age group, so you can do 1 minus that age group and get 0.43 or 43%. The other possibility is just to take all the categories that are not 18 to 23 and add them together. And you will still get 43%. A deck of playing cards has 52 cards, of which 12 are face cards. If you shuffle the deck well and turn over the top 3 cards one after the other, what's the probability that all 3 are not face cards? So we know there are 52 cards in the deck, and of those, 12 are face cards. If we flip one card over, we now only have 51 left in the deck. And if the first one we flip over is a face card, we know that there's only 11 left in the deck that are face cards. Now we've already flipped over 2 cards. The number of cards still left in the deck are only 50. If we've already pulled out 2 face cards, the number of face cards that are left would only be 10. And if we multiply those together, we're going to get 1,320 over 132,600 different combinations, or the probability that the first 3 cards that are dealt are all face cards is 0.995%. So a little under 1% chance that the first 3 cards will all be face cards.